Hello students, welcome to this session. In the previous videos, we have discussed the line integral of a vector valued function. Then we have discussed Green's theorem in a plane, which established the relation between the line integral and that of double integral over the region R. Then we have discussed Stokes' theorem, which gives the relation between the line integral and that of surface integral. In this video, we have to discuss the Gauss divergence theorem, which will establish the relation between the surface integral and that of the volume integral. If V is the volume bounded by the surface S and F bar is a continuously differentiable vector function, then the double integral over the surface S F bar dot n cap ds is equals to the triple integral over the volume V divergence of F bar into dV, where dV is the differential of the volume and is generally given as the product of dx dy dz, where n cap is the outward unit vector normal to the surface S. And the left hand side, which is the statement of the Gauss divergence theorem, and the left hand side, that is the double integration over S F bar dot n cap ds, will represent the surface integral, and the RHS, that is triple integral over the volume V divergence of F bar into dV, represents the volume integral. That's why this Gauss divergence theorem represents or establishes the relation between the surface integral and that of the volume integral. And as usual, again, the scope means proof is beyond the scope of the syllabus. Directly we have to concentrate on the examples directly. And the first example, okay, employ Gauss divergence theorem to evaluate double integration over the surface S F bar dot n cap ds, where F bar is given by x square minus yz into I plus y square minus zx into j plus z square minus xy into k, taken over the rectangular parallelepiped where x lies between a and b, x lies between 0 and a, y lies between 0 and b, and z lies between 0 and c. Now, according to the Gauss divergence theorem, we have the surface integral equals to the triple integral over the volume V divergence of F bar into dV. That means, first of all, we have to find the divergence for the given vector, and the given vector is F bar equal to x square minus yz into I plus y square minus zx into j plus z square minus xy into k, which is of the form f1 into I plus f2 into j plus f3 into k, where f1, f2, f3 are the components. Now for a given vector f bar, which is of the form f1i plus f2j plus f3k, the divergence of f bar is given by dou f1 with respect to x partially plus dou f2 with respect to y partially and dou f3 with respect to z partial. Now, if we calculate divergence of f bar, means if you differentiate the first component with respect to x, it will give 2x, and this will be 0. And if you differentiate the second component with respect to y, it will give 2y, and the derivative of third component with respect to z is 2z. And if you take 2 common, it will be x plus y plus z. Now, 1 reduces to that. 1 is nothing but the statement of the Gauss divergence theorem. If you use the value of divergence of f bar on RHS, we can write like this, that is triple integration over the volume V 2 times x plus y plus z into dx plus dy plus dz. 2 is a constant, it can be taken outside. Now here, the order of the integration is first with respect to x, next with respect to y, next with respect to z. Now first we have to set the limits with respect to x, and we know x varies between 0 and a, that's why x varies between 0 and a. And now we have to set the limits for y varies between 0 and b, and the third one, z varies between 0 and c. If we go on integrate, that is 2 times, keeping these two as it is, x with respect to x is x square by 2 plus yz is a constant. Now it has to be integrated with respect to x, that is 1 into x is x. You have to take the limit from 0 to a, and next you have to integrate with respect to y, then with respect to z. Wherever x is there, if you take a, it becomes a square by 2 plus y plus z into a. Since lower limit 0, that goes 0. Now let us integrate with respect to y now. That is a square by 2 is a constant, 1 with respect to y is y. plus a is a constant, y with respect to y is y square by 2 plus multiplying az becomes constant, 1 with respect to y is y, and we have to take the limit from y equal to 0 to b, and the resulting has to be integrated with respect to z. Now to as it is, z varies from 0 to c, and this becomes upper limit b, that is a square b by 2 plus ab square by 2 plus a b into z, because here the substitution is with respect to y and you have to take y equal to b upper limit. When we take lower limit, all the terms consist of y, it reduces to 0, you have to ignore that. Now this has to be integrated with respect to z. Now this becomes a square b by 2, okay, into z. Okay, 2 is as it is constant. Now here it is ab square by 2 into z, and ab is a constant, z with respect to z is z square by 2, and we have to take the limit from z varies from 0 to c. If we take 2 as LCM, 2 will get cancelled here. This becomes a square b. Now let us take the upper limit and taking 2 common. Taking 2 common, these will get cancelled. Wherever z is there, if we substitute, we get this one as a square bzc plus ab square into c plus ab into c square. Now among these, if you take ABC as common, here we'll have to a plus b plus c. That will be the value. Finally, the required value of the surface integral, that is double integration over s, f bar dot n cap ds is given by abc into a plus b plus c. That will be the required value of the surface integral. Now let us go to one more, which is of the similar kind. If f bar equal to 2xy into y plus y square into j plus xz into k, and S is the rectangular parallelepiped bounded by x equal to 0, y equal to 0, z equal to 0, and x equal to 2, y equal to 1, and z equal to 3, and evaluate, that is again we have to evaluate double integration for the surface S, f bar dot n cap ds. Now by Gauss divergence theorem, we have, that is f bar, that is double integration over S, f bar dot n cap ds equals to triple integration over the volume V, that is a divergence of f bar into dv. That's why again, first of all, you have to find the divergence for the given vector. The given vector is this one, which is of the form that is f bar equal to 2xy into I plus y square into j plus zx into k, and that one equal to f1i plus f2j plus f3k, where again, if you differentiate the first component with respect to x, it will give 2y, and second component with respect to y, that becomes z square, and third component with respect to z is given by x. Therefore this is the divergence of f bar, because if f bar is a vector of the form f1i plus f2j plus f3k, then the divergence is given by partial derivative of f1 with respect to x plus partial derivative of f2 with respect to y plus partial derivative of f3 with respect to z, and that leads to this one. Now taking this value in RHS of 1, we can write like this. And as we know, dv can be given as dx, dy, dz, or any of the combination, but what combination we take, accordingly we have to set the limits. In earlier cases, we have taken the means the order of integration as, that is dx, dy, dz. That's why first you have set the limits for x, then y, then z. And in this case, you have taken the order according to our convenience. We can take first z, then y, then x. Now z varies from 0 to 3. That's why I have written z varies from 0 to 3. Then y varies from 0 to 1. That's why I have written. And x varies from 0 to 2. Now once you go on integrate, we can write these two as it is. That is 2y with respect to z means 2yz plus z square with respect to z is z cube by 3 plus x as it is. Sorry, x as it is. Now 1 with respect to z is z. But to take the limit from 0 to 3. Then with respect to y, then with respect to x. Now x varies from 0 to 2, y varies from 0 to 1. This as it is. Take the upper limit. Wherever z is there, we have to take 3. That becomes 6y, and thus becomes 27 by 3, 9, and this becomes 3x. Since lower limit is 0, all the terms reduces to 0 into dy dx. Now this has to be integrated with respect to y, and we have to take the limit from 0 to 1. 6 as it is, y with respect to y is y square by 2 plus 9y plus 3xy, and in this case y varies from 0 to 1, and the resulting has to be integrated with respect to x. Now if you take y equal to 1, that becomes this is 3 by 2, sorry 6 by 2, that is 3, plus 9 plus 3x since lower limit is 0 and all the terms reduces to 0 with the y equal to 0. And this has to be integrated with respect to x, that is 3 plus 9, that is 12, with respect to x is 12x plus 3 as it is. X with respect to x is x square by 2, and we have to take the limit from 0 to 2. And once we take the upper limit, this becomes 24 plus, that is 6 we get, with lower limit both reduces to 0. 26 plus 4, that becomes 30. Therefore, in this case, the required value of the surface integral is given by 30. That will be the way how we can use the Gauss divergence theorem in order to evaluate the surface integral for the given surface. Now let us go with one more example. Using Gauss divergence theorem, evaluate double integration over S a bar dot n cap ds, where a bar is given by x cube into I plus y cube into j plus z cube into k, where S is the sphere x square plus y square plus z square equals to a square. Now, according to the Gauss divergence theorem, we can write the required value of the surface integral, that is double integration over S a bar dot n cap ds equals to triple integration over the volume V divergence of a bar into dV, where a bar is the given vector, that is x cube I plus y cube j plus z cube k, which is of the form f1i plus f2j plus f3k. Now, if a bar is a vector of the form f1i plus f2j plus f3k, then the divergence of a bar is given by partial derivative of f1 with respect to x plus partial derivative of f2 with respect to y plus partial derivative of f3 with respect to z. And in this case, if we differentiate the first component with respect to x, that becomes 3x square, plus second component with respect to y, that is 3y square, third one, that is 3z square. If you take 3 common, it gives you 3x square plus y square plus z square. And in this case, the given curve or the surface is, that is x square plus y square plus z square equals to a square. Okay, now if you substitute this value of divergence of f bar on RHS, we can get like this, that is 3 into x square plus y square plus z square, and dv is given by dx dy dz. Now, in order to evaluate this integral by taking the limits for xyz, it becomes tedious. That's why we can evaluate this triple integral using the spherical polar coordinates easily instead of direct evaluation. Now the spherical coordinate substitution says x equal to r sine theta cos pi, y equal to r sine theta cos pi, and z equal to r cos theta. And dx dy dz is r square into sine theta into dr d theta d pi, and x square plus y square plus z square equals to r square. If you square and add this, it results in r square. And the limits for the first polar coordinate, that is r, lies between 0 and a. The second one is theta, which lies between 0 and pi. And the third one pi, that lies between 0 to 2 pi. Now, once you take these substitutions by saying d pi d theta dr as the order of integration, therefore first you have to set the limits for pi. Pi varies from 0 to 2 pi, and now theta lies between 0 to pi and r lies between 0 to a. And now here it is 3 into, okay, x square plus y square plus z square, that is r square, and dx dy dz, that is given by r square into sine theta into d pi d theta dr. Okay. Now, if you take 3 common, r varies from 0 to a, theta varies from 0 to pi, r raised to 4 into sine theta. These are constants with respect to pi. And now d pi, integration of d pi is pi, and you have to take the limit for pi from 0 to 2 pi, then into d theta into dr. Now, if you take the upper limit, that becomes 2 pi minus 0, and it is dr. And once you integrate with respect to theta, integration of sine theta is minus cos theta, and the limits for theta are 0 to pi. This is 3 as it is. Okay, and if you take 3 into 2, that is 6 pi. If you take the along with the negative sign, that becomes 6 pi. R varies from 0 to a, r raised to 4. And once you take the upper limit, that becomes cos pi minus lower limit, that is cos 0 into dr. Now this is 6 pi, and this becomes minus 1, and this is 1. That becomes minus 2. That we are written here. Now integration of r raised to 4 with respect to r is r raised to 5 by 5, and you have to take the limit for r from 0 to a. That is, this becomes 12 pi 12 pi by 5, and if you take the upper limit, that is e raised to 5 minus 0, and the final answer is that is 12 pi e raised to 5 divided by 5. That is the required value of the surface integral, that is a bar. Instead of f bar, we can write here a bar, that is double integration over s, that is a bar dot n cap ds. Its value in this case is given by 12 pi e raised to 5 by 5. And now one more last, which is there in the model question paper also. And the question goes like this: using Gauss divergence theorem, evaluate double integration over s f bar dot n cap into ds over the entire surface of the region above xy plane bounded by the cone z square equal to x square plus y square and the plane z equals to 4, where f bar is given by 4xz into I plus xyz square into j plus 3zx. Now by Gauss divergence theorem, first we can write on the statement, that is double integration over the surfaces f bar dot n cap ds equals to triple integration over the volume V, divergence of f bar dot dv, where dv is given by dx dy dz. And the cone z square equal to x square plus y square is going to be like this. This is x axis, this is y axis, this is z axis. And the cone equation of the cone is given as z square equal to x square plus y square. And now, once we get the orthogonal projection of this represents a circle, and this is a surface z equal to 4. If you take z equal to 4, that gives you x square plus y square equal to 60. Now, they have given the vector f bar like this, that is of the form f1i plus f2j plus f3k, and the divergence of that one is given by partial derivative of f1 with respect to x plus partial derivative of f2 with respect to y plus partial derivative of f3 with respect to z. And once you differentiate the first component with respect to x, that gives you 4z. The second component with respect to y, that is xz square, plus the third component with respect to z is 3. Now once you substitute this, okay, first I will write the limits for x and y as it is. Only as we have taken the order of integration as dz dy dx, and divergence of f bar is given by 4z plus xz square plus 3. First I will set the limits for z, and in this case the limits for z are, okay, that is very evident, that it can be given as if you take the limits for here, if you take the limit and z equal to square root of x square plus y square to 4, up to 4, you take any point on this line, okay, z value is given by square root of x square plus y square up to z equals to 4. That's why we have taken the limit for z equal to square root of x square plus y square to 4. Then we have to integrate this one with respect to z, and we have to take these limits. Therefore, 2 means if you integrate z with respect to z, z square by 2, that gives you 2z square plus x z cube by 3 plus 3z, and z varies from square root of x square plus y square to 4 into dy dx. Later on we can set the limits for x and y, and now I can take first y then x. Accordingly we have changed the order of integration as dx dy. Now here, if you take z equals to 4, that becomes 4 square. That is 2 into 4 square plus x as it is 4 cube by 3 plus 3 into 4 upper limit minus lower limit means wherever z is there, if you take square root of x square plus y square, we are going to get this one. Now again, if we go on evaluate this one directly, that seems to be somewhat difficult. Let us go with polar coordinates. Okay, converting into polar coordinates. Now over the circle x square plus y square equal to 16, we can set the polar coordinates x equal to r cos theta and y equal to r sin theta. Accordingly, dx dy gives you r into dr d theta. And this type of evaluation converting into polar coordinates, hope so we have studied in the first semester. There we evaluated double and triple integrals. Okay, now the variation for r. Once you look at this, this is a radius. Radius varies from 0 to 4. Okay, that we have written r varies from 0 to 4. And in order to cover this entire region, that theta must vary, take one full circle means theta varies from 0 to 360. That's why we have written theta varies from 0 to 2 pi. Wherever x is there, you take r cos theta. Wherever I is there, we take r sin theta. Therefore, this value is that is 16 into 2, that is 32, and this is 4 cube by 3 as it is x equal to r cos theta, and this is 12 minus this becomes 2r square plus this is x r cos theta by 3. Now x square plus y square is r square raised to 3 by 2 plus this is 3r. Then dx dy is given by, as you have written here, r into dr d theta. Now r varies from 0 to 4 and theta varies from 0 to 2 pi. And this is 32 plus 12, that is 44 plus 4 cube by 3 r cos theta minus, and that is 2 r square plus r raised to, because once you take this one, 2 will get cancelled, r cube into r, that is r raised to 4 by 4, sorry 3 into cos theta, and this 3r as it is, that is r dr d theta. Now once if you take the integration with respect to r after multiplying each term by r, this is 44 into r, that is 44 as it is, r with respect to r gives you r square by 2, is 4 by 3 as it is, cos theta also as it is. Now r into r square, when you integrate with respect to r, that becomes r cube by 3 minus, if you take the product 2, r square into r is r cube. Okay, with respect to r is r raised to 4 by 4. Again, cos theta as it is, r raised to 4 into r raised to 5. R raised to 5 with respect to r is r raised to 6 by 6. R raised to 6, 6 into 3, that is 18, minus, after multiplying this becomes minus 3, r into r square. With respect to r is r cube by 3. We have to take the element for r varies from 0 to 4. The resulting has to be integrated with respect to theta. Now this is 44, take the upper limit, that is 4 square by 2 plus this becomes 4 raised to 3, and once you take r equal to 4, that becomes 4 raised to 3. Totally that becomes 4 raised to 7 by 9 into cos theta, and this becomes r raised to 4 by 4 means 2r raised to, sorry, 4 raised to 3 minus, if you take r equal to 4, that is 4 raised to 6 by 18 into cos theta, and this becomes 3 get cancels, r is 4, that is 4 is to 3. With lower limit, all the terms reduces to 0 because each term consists of 0 r, and you have to take r equal to 0. Now this becomes like this. Now this has to be integrated with respect to theta. Now in these two, this as it is, okay, that becomes 22 into 4 square, and in this and this we can take cos theta as common, we can write, and if you simplify this, that becomes minus 3 times 4 raised to 3. Resulting has to be integrated with respect to theta. Now this is constant, and product means it is coefficient is 1 with respect to theta is theta, that is 0 to 2 pi, because 4 square is 16 plus this as it is, and you have to integrate this one with respect to theta, or the limit 0 to 2 pi minus 3, and this is 4 cube is 64. 1 with respect to theta is theta. You have to take the limit from 0 to 2 pi. And now when we integrate this one, that becomes sine theta. And if you take the upper limit and lower limit, this reduces to 0. Therefore, the value of this integral is 0. 0 to something is 0. That's why we ignore this entire second term. And once you take this one, this becomes 2 pi. And once you take here theta equal to 2 pi, it will give 2 pi. And in these two, if you take 32 pi as your common term, therefore here we get 22 pi. Pi is also taken, so simply you'll get 22. And here, if you take 32 pi as the common term, that is 3 into 2, that is 6 into 2, that is 12 will get, and the simplification is 22 minus 12, that is 10, that is 32 pi into 10, that is 320 pi. That will be the value of the required surface integral when the curve z square equal to x square plus y square, and the plane z equal to 4, where f bar is given by this, which is taken above the xy plane. That will be the required value of the surface integral for the given surface integral. And this is all about that vector integration. And we have started from vector line integration, and then we have studied that Gauss divergence theorem. Sorry, first one is Green's theorem, which will give the relation between the line integral and that of the double integration, which helps to evaluate the line integral easy. Next one, we have studied the Stokes theorem, which will give the relation between the line integral and that of surface integral. And the third one, Gauss divergence theorem, which will give the relation between surface integral that of the volume integral. And each theorem has their own importance and applications in various branches of engineering, especially electrical, mechanical, and that of electronics. They play a very crucial role in these fields. Wherever we come across with vector notations, this theorem plays a very important role. This is all about that first module, which covers some of the concepts of vector differentiation like gradient, divergence, curl, and when you come across with integration, where means vector integration, you have studied the line integration, Green's theorem, Stokes theorem, and that of Gauss divergence theorem. Thank you.